Hello. So now let's see, we're going to talk about the last component of this sort of deep dive here relating to Megatron using DeepSpeed and Zero. So one thing I wanted to point out first is we have some tutorials on our DeepSpeed website that I urge you to check out. So this is going to go into a lot of the specific code changes that we made to NVIDIA's Megatron code to use DeepSpeed and use Zero and that sort of stuff. I won't go into too much of those details right now due to time, but I do want to cover one specific piece, and that is here. So inside the entry point script of Megatron, where we're actually going to do the training, we do our DeepSpeed initialize just like any other model. However, there's one kind of special piece that we pass called this MPU object. It's this model parallel sort of object. And what this does is it's unique for any model that's set up to use model parallelism. So Megatron, for example, is set up to use something that's commonly called like tensor slicing kind of approach. And what that does is it splits certain specific tensors in the model, and those specific parameters in the model across several model parallel GPUs. So let's say we're running with eight GPUs, and we let's say have a model parallelism degree of 4. So that means that our actual model, let's say our 4 billion parameter size model, is split across four GPUs. Then to do 2 instances of data parallelism, we would then make sort of 2 copies, I guess, of that model that's split over 4 GPUs. So it would be a 4x2 kind of setup. So if we had a batch size of 8, let's say, per model parallelism unit, then that would mean that we'd only have sort of 2 of those. So it'd be the batch size of 8 times 2, 16 overall batch size. But I digress there. So let's see. So the MPU that we're passing in here is just this object that tells us which ranks in our job that we're running, which GPUs are associated with which data parallelism unit or which model parallelism unit. So we know kind of how to, let's say, all reduce the gradients across the correct data parallelism ranks and so forth. Okay, so for this experiment, we're going to run a 4 billion parameter model with Zero and DeepSpeed, and without it, using just baseline Megatron. However, I wanted to run this experiment with 32 GPUs. So part of the reason behind this is, as Sam discussed earlier about Zero, as we scale up the number of GPUs specifically our data parallelism degree, we can then offload and partition the extra optimizer and gradient state required. So we kind of get more headroom for batch size, more headroom for model size, all these things as we kind of scale out that degree. So with that in mind, we're on a different cluster here. So this is a DGX2 cluster. This is, for example, if you've read or will be reading our Zero paper, all of the experiments in that paper were done on these nodes here. So what's special about this over the previous nodes that we had was, in this case, we are running 16 V100s, 32 gig per card, and we also have 8 InfiniBand cards. So there's 800 gigabit per second InfiniBand as well. So that's great. So let me kill anything running in the background here. And moreover, we can see in this case, we have 2. So if we look at our job host file, just like before, we have 2 worker nodes, but this time each worker has 16 slots for a total of 32. Okay, so now we have 2 different things here. So we have our, in scripts, we're going to look at our baseline. So this is going to run baseline Megatron with a model parallelism degree of 4. And this is a 4 billion parameter model. So these are the sort of specific architecture of this model. So number of layers, 64, hidden size, number of tension heads, etc. Let's see, we're going to use the DeepSpeed launcher just so as a convenience to be able to launch this job across all these 2 nodes. But DeepSpeed is not actually going to be used in the code itself. So we don't have the DeepSpeed flag is not passed here to enable it in this code. Right, and then if we look at, so yeah, let's go ahead and do this. And with this model, I know because prior sort of done the searching of a kind of binary search problem was trying to find the largest, sort of most efficient batch size and the best model parallelism degree for this 4 billion parameter model. We found, at least in this case, it's a model parallelism 4 and a batch size of 8. So let's go ahead and run this, and we can watch the log here. So as we see, yeah, the world size here, 32. So we have these 32 ranks. That's looking good. Running on 2 different nodes. We see worker 1, worker 0. Lots of different configuration parameters. This is another tab into the same machine, so we can even just watch NVIDIA SMI here to see kind of how things are going. Starting to allocate some memory. Okay, now this part, it's going to take a little bit of time. What this is doing is actually building the model across all the different GPUs, and since it's a 4 billion parameters, it takes a little bit of time. So maybe the final video here, maybe I can fast forward a little bit of this, make this go by. But if you'd like, maybe you can even fast forward past this part if this is getting a little boring as it's loading. While it's loading, maybe let me load model. And so in this version of the model, what we did was modify the code so that we can run kind of DeepSpeed versus the original baseline, but just adding a few flags and these branches to say, like, if we're in this DeepSpeed mode, do the DeepSpeed things, and otherwise use kind of the original code. And while that's loading too, is so a lot of the details here in terms of checkpointing and a few different features that DeepSpeed has that we've found work really well for some large models, such as activation checkpointing. Here's some evaluation. Cool, here we go. So we've now built this model. Now remember, this is a model parallelism degree of 4. So each of those ranks in a model parallel unit has about 1 billion. So if we bring up our calculator, we did this, so it's times 4 is about 4.2 billion, right? Close that. So one tricky part here is that not all models are already set up to do model parallelism. So techniques like tensor slicing in this case requires kind of very specific kind of implementation, typically for this type of model. So like you have to kind of know which parameters you want to slice, how you want to do it. It's kind of it's not a black box kind of. Can't treat the model essentially as black boxes as much as you could other techniques. Whereas like data parallelism, for example, very sort of clean. Like you don't need to necessarily know anything about the model. Just average the gradients across your ranks, and you're good to go. So if you have the ability to run a model without model parallelism, that typically is sort of much more preferred because it's a much more sort of easier time on the developer's cost to adapt to new models and that sort of thing. So that's one of the big motivations of Zero and DeepSpeed is that, as you'll see in a little bit, this model we run with model parallelism 4 in the baseline, but Zero is actually able, where DeepSpeed with Zero is actually able to run this without model parallelism at all, and we have model parallelism degree of 1, which essentially is no model parallelism. So cool. So let's see what we're seeing now is we see we've passed 5 iterations. We're at 10th iteration. Got some samples per second here. Let's let it go a little bit longer. And we'll make a note here. So baseline, this is a 4 billion parameter model. Model parallelism 4, batch size of 8. And that's hitting about, well, let's wait for it to stabilize here. It's kind of jumping around, so samples per second is what I'm watching. 6 at the beginning, 28, 27, 16, 25. We can even see, since we have this wall clock breakdown, like where some of this might be coming from, but it seems like maybe there's 225s. Good. Okay, let's call this a 25. I'll say 25.8. Okay, so now let's go ahead and kill this. And I'll show you the DeepSpeed version. Make sure everything's killed okay. Okay, let's now bring up DS. Show you the scripts folder here. So scripts, DS02, pre-train. Okay, so now in this case, like I was mentioning before, is we're going to run this with model parallelism 1 with DeepSpeed and 02. And looks like we're getting, there we go. So same model size, parameters. We're going to use this configuration JSON, which I'll bring up next. We have some other features. Let's see. So we're going to run with DeepSpeed. I'm going to pass in this DeepSpeed config. Gonna use DeepSpeed's activation checkpointing feature. And now let's bring up the JSON. Okay, so we are going to use zero optimization stage 2. So this partitions the optimizer state and the gradients. We are going to do FP16, some activation checkpointing flags. We're going to do a few different things here. Now, what else? So now we can actually run this. Let's make sure. I like to also double check that. Cool, so nothing's happening on the GPUs, that's great. So scripts, DS, 02 pre-train, and I know with this configuration, should be able to run a bigger batch size as well. So same number of GPUs, so it's 32 GPUs, but we're running 2x the batch size and model parallelism degree 1, which means we're just doing data parallelism. So our total batch size is also bigger. Let's give this a shot. So DeepSpeed plus 0.2, 4 billion, same model, more parallelism 1, batch size 16. Let's see what we get. Thing I'll point out here too is we have in the DeepSpeed config.json page, we have several zero optimizations for training. You can turn on and off different features. Lots of descriptions here of like which ones, like what they do, all that. So if you remember, like last time, it does take a little bit of time to actually build the model for the first time. So we'll see that soon. We'll make some more progress here. Oh, additional thing. This DGX2 has a lot of CPU as well. See, it's hard at work here. 96 cores, always fun. And it also has about almost 1.5 terabytes of memory, which is nice. Now, DeepSpeed and Zero aren't really taking advantage of that during training at all, but it is nice. Nice is there for various reasons for those boxes. Okay, here we go. So this is number of parameters in the model. So we show just rank 0 has essentially the same number of parameters as the other, about 4.2 billion. We should start training shortly. What's nice is in addition to just being able to turn on and off 0 with like just a different configuration in your JSON, you can switch between the modes. So you can switch between our 0 stage 1, which only does optimization partitioning, and then also switch to 0 stage 2 if you want to try that out. Yeah, let's see, it looks like we're just about to start. See what the performance looks like here. So after this, I'll show you guys one more thing. I'd previously run on the same setup, same nodes, an 8 billion parameter model with these 32 GPUs. It just takes so long to start these up that I didn't want to do it live. But I'll show you the logs and we can kind of step through them and show you what the performance we got with baseline versus what we get with 0 with DeepSpeed. But I figured I'd at least show you some of this live. So cool, yeah, so it shows you 0 optimization stage 2, all these fun parameters that we had in our config. Let's just start in here. So let me bring up config really quick. Steps per print 10. There we go. we're just getting into iteration 5, so we're 36. Reference, so we're at 25. Let's wait to get a couple more steps in here. Actually see here too the memory that's actually allocated during debugging. That's sometimes quite useful in terms of the allocated memory, the max that's been allocated, cache, all that kind of fun stuff. All right, we're bumped up to 39. Okay, so 39, and now let's go ahead and switch to a different config. So in addition to the 4 billion parameter run that we just did, we can, I also saved a previous log from a 8 billion run. So if we, just to save time, we'll just kind of bring up the logs here and show you kind of some of the highlights here. So the first one is the baseline. So let's look at the baseline. So it's baseline 8 billion. In this case, we're using a model parallelism of 8, batch size of 8, and using the same 32 GPUs that we used for the first run. And we can see, I'm just kind of scroll through this, just like how it ran before. So we see that there's 8 model parallelism ranks. Each one is about a billion parameters. And if we do our fun math here, just to see the exact, about 8.3 billion. Now, what else do we see? So we see samples per second seems to stabilize at about 11.9 or so samples per second. So if we bring that up here, so this is the baseline 8 billion model parameter, or model parallel 8, batch size of 8, and what did I say that was? That was 11.9 samples per second. Now we also have a DeepSpeed run with 0.2, and we have the log here. Now in this case we ran 8 billion parameter model parallelism 2, so we still used some model parallelism, batch size of 16, and the same 32 GPUs. So let's write that down. So we got 8 billion model parallel of 2. We can actually see that here as well. Let's find, there we go. So there's model parallel 2, batch size of, what did I say, 16? Let's go and search for batch. There we go, batch size 16. Excellent. So batch size 16. And what's our throughput? Let's scroll down. When it starts, a lot of just paging through here. There we go. So samples 18, 19, 20, 20.8, 20.4, 20.9, 19.8. Yeah. Let's do, I don't know, something like 19.5 or so. So in this case, uh, 1.6x improvement, which is great. All right, so that essentially concludes our deep dive with DeepSpeed. We went over BERT large in a lot of detail. We went over Megatron with Zero and DeepSpeed in a bit of detail. I urge you to check out DeepSpeed post any questions you have also on our issues, our GitHub issues, that sort of thing. I believe we also have some kind of live Q&A through KDD. If you're watching this video for KDD, feel free to ask questions there. Otherwise, GitHub issues, great spot. Thanks so much.